Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we are going to discuss on chapter 2, Kinematics. Now, kinematics essentially is a description about how objects move. So essentially, it's the motion of objects. Okay. However, before the beginning of this chapter, I need to warn you guys, everyone, that this chapter is highly mathematically intensive. Okay. Now, in the past, in ancient times, when people try to do science, when they describe the scientific phenomena in the world that they see, they more often than not they use words, right? They use descriptions to discuss science. So, for instance, okay, in the past, in ancient Greece, there's this guy called Aristotle. Okay, he's a very famous thinker. He was quite interested in the science around him, and he asked a lot of questions and he tried to answer many questions. So, for instance, if he sees a ball rolling on the floor, we all know that eventually the ball will stop rolling. So, how do we explain that? Well, today we know that it's due to friction. Right? We see a ball, okay, rolling on the floor, and you know that today there is a frictional force. This is why the ball eventually will stop. But to him back then, there wasn't such an idea of friction. So he tried to explain the fact that the ball stopped rolling after a while by saying that objects tend to get tired. Objects tend to get tired after a while, so this is why they stop. Well, today we may laugh at it, but back then, I think that was a great thinking. The fact that he actually asked and he thought of the answer, that was really great, right? But back then, they all use words to describe science. But since Galileo Galilei, this guy here, this man here, okay, in 1890, he married the idea of mathematics and science. So he started describing motion of objects in mathematical form. So today, from then onwards rather, physics or science in general is closely tied with mathematics. Yeah. So this chapter is going to be mathematically intensive. I need you to summon all the math knowledge that you already have. Okay. In particular, as you can see here in part 1, you need to know about graphs because for the second part of the video, which is coming soon, we will discuss about the motion of objects in graphs. You can see how it can be plotted in graphs and what information we can obtain from graphs regarding the motion of objects. Alright, so without further ado, let's get right to it. So in part 1, rather in section 0, okay, we need to discuss the mathematical knowledge that you need, right? If you already know all these things, by all means, please skip. Alright. So first of all, we learned already that a straight line graph has a general equation of y equals to mx plus c. Okay, for m being the gradient, okay, and you can calculate the gradient using this formula: y2 minus y1 over x2 minus x1. So, and then c is the y-intercept, yeah? Okay, so how do I calculate gradient? So if you are given a graph, all you have to do is to find two coordinates that lie on the graph. So, and try to find two that are convenient. So for instance, I have chosen this and this point here, okay, as the 2 points that I'll take reference to. So all I have to do is note down their coordinates. Okay, on the graph itself or by the side, it's fine. So choosing 2, 5, and 10, 21 as the 2 points to calculate, I input the y coordinates y2 and y1, okay, being 21 and 5. And then, so over here, I chose 10, 21 as my x2, x y2, sorry, x2, y2, and 2, 5 as x1, y1, yeah? So immediately you can put it into the formula and you can get out the gradient. So recall, I can also choose 2, 5 as x2, y2, and 10, 21 as x1, y1. No problem, I can also do that. But just make sure that your 2 and 1, this 2 here and 1 here, are consistent with each other. Okay, you can go ahead and try on your own. If I choose 2, 5 as x2, y2, you should get the same result, which is m equals to 2. Okay, so I have obtained m in the equation, which is the gradient. Now, Next, I need to find the the y-intercept of the graph. How do I know that? Well, I simply go to the graph and I see, oh, okay, the graph cuts the y-axis at this point, which is 1. So my c equals to 1, and I'm done. So all I have to do is to plug in the numbers into the general equation y equals to mx plus c, and I get the equation of the graph. So this is something that I believe you should already know. Okay, if not, please go ahead and practice more. So here I have 2 practices here for you to try. All right, now before we begin, I need to tell you the hint. The hint here says check the axis title. Now, when I look at the graph, the first thing I go to that I look at, okay, any graph, like let's say this one. Let's go back to this one. Now, when I see a graph, the first thing that I would check, that I will read, is the axis. Okay, because without the axis titles, this graph has absolutely no meaning. All right, and sometimes there are tricks inside. So sometimes the units you need to pay attention to. All right, so I check the axis is y and x, but for this one, if you pay attention, you will see that it's d and t instead of y and x. So my general equation for this graph is no longer y equals to mx plus c. That is not true anymore because it's no longer y and x. Instead, it should be d equals to mt plus c. Can you see that? My y-axis has been replaced with d, and my x-axis has been replaced with t. So you need to pay attention to the axis. Okay, go ahead. So next thing is I'll go ahead and choose 2 convenient coordinates, which I have already chosen. These 2. Okay, so I will choose the top here to be x1, y1, and the bottom here to be x2, y2. Again, you can do the other way around. It should still be the same. Okay, so d equals mt plus c. I need to find m first of all. Okay, so I write down the general formula: y2 minus y1 over x2 minus x1, and I input my values here. Okay, so y2 is 0, y1 is 30 over x2 is 10, and x1 is 0. And you do your calculations, you should get negative 3. So the gradient here is negative 3 because you can see that it's downward sloping. Yeah. Okay, next is the y-intercept. Okay, so what's the y-intercept? Go in and take a look. Oh, it's 30. Alright, so c equals to 30. So I have all the information that I need. My general equation of the graph is d equals to negative 3t plus 30. Voila, we're done. Okay, is that easy? Okay, next one. Okay, so for this graph, you can see that, okay, it is y against x. So the general equation should be some form of y equals to mx plus c. But you can see I've already written down the general equation. Sorry, rather the equation of the graph. This graph is y equals to 4. How do I know that? Well, if you recall, what is the gradient of a horizontal line? It is actually 0. Okay, the gradient of a horizontal line is actually 0. If you do not believe me, you can go ahead and choose 2 convenient points, for instance, and go and calculate the gradients. Yeah, so the general equation y equals to mx plus c. So my m is 0 because it's a horizontal line. Again, check for yourself. Okay, prove that it is indeed 0. So generally y equals to c. So what is the y-intercept here? You can see that it's 4 right over here. So c equals to 4, and hence the equation is y equals to 4. Very simple. Okay, next, moving on. Okay, gradient, right? We just calculated gradient using this formula, y2 minus y1 over x2 minus x1. Now, if you have learned well in your mathematics class, you will know that in general, gradients do not carry units. Okay, because it is a mathematical idea, it's just a number. Okay, but in science, depending on what is the axis, okay, this gradient may carry meaning, may have some meaning. Okay, or rather, sometimes it might have some units also. Okay, so why is that so? Because the idea here, the grand idea here is gradient is a rate. Okay, what does it mean by rate? For instance, if I look at the graph here, y-axis is number of grapes eaten and x-axis is time. Okay, and as some data here, I can draw a straight line. Now if you calculate the gradient here to be 3, question is, what does the gradient mean here? Is there a meaning to the gradient? Yes, this gradient tells me that I know the person or rather, okay, yeah, the person eats. You don't have to take this down, yeah. It's 3 grapes every second, right? It's 3 grapes per second. So can you see that grapes per second is a form of, it's an example of a rate, something per second or something per hour, something per minute is always a rate. Okay, so the gradient here tells me that it's a rate, and you realize that the gradient here has a unit, number of grades per second, right? So depending on the axis again, your gradient may carry a unit. Okay, so let's go back to the previous graph in page 1. Let's go back to the previous graph. Okay, now this one. Okay, now let's look at this. If I tell you that d is now representing distance, okay, and it has a unit of meters, for instance, and now t represents time, and now it has a unit of seconds. Now, can you tell me what is the meaning of the gradient? Okay, if you get speed, then great. But in case you have absolutely no idea, let's see why is it speed. Okay, now because if I go and calculate the gradient, okay, the y is in meters because the you know these two guys are distances, right? Distance, and these two must be time because that's the x-axis. The y-axis is distance, the x-axis is time. So each of them will carry a unit, right? So the y, so-called the y, which is d, carries unit of meters, and the t carries units of seconds. So if you recall your chapter 1, right, you take meters, a meter quantity divided by a second quantity, your final unit should be meter per second. Alright, so the number is 2, but the units is meter per second. So meter per second, what kind of quantity is this? What quantity has the units of meter per second? Well, if you're quick enough, you will tell me that it is speed. Speed has the SI unit of meter per second. Alright, so you realize that, oh, in this special case, you know, if my y-axis is distance and my x-axis is time, you realize that the gradient actually has a meaning of speed. Okay, this is something we will see in the last part of the video. Sorry, rather the next video, the last part of the chapter. Alright, so heads up first. Alright, so we have done with the mathematics part. Okay, we will come to the first section of the chapter, distance versus displacement. Now, in this part of the video, you will be able to tell me, rather at the end of this section, you should be able to tell me what is the meaning of scalar quantities and what's the meaning of vector quantities. Okay, and state the difference between these two quantities, scalar versus vector. Okay, so let's get right to it. Part 1, scalar versus vector. So when we talk about quantities and physics, recall, when we talk about quantities, we need a magnitude in general, magnitude and units, right? Okay, so for instance, unit. Okay, so for instance, 5 kg, right? This 5 here is the magnitude and kg here is the unit. Okay, now that is for scalar quantities. Okay, for vector quantities, you need another ingredient. You need to tell me another piece of information. Okay, what is it? Okay, let's take a look here. If I tell you the following, to do the following thing, move 2 meters from where you are. Try, move 2 meters from where you are. You'll probably tell me, huh? Question mark, question mark, question mark. In which direction? because you can simply move forward, backwards, to the left or to the right. Alright, so in this case, this move 2 meters from where you are doesn't make sense because I did not give you the direction. So in this case, there are certain physical quantities that make sense with direction. I need to give you a direction, if not it doesn't make sense. So these kind of quantities are what we call vector quantities. Okay, so vectors need to carry a direction. Next thing, if I tell you now, my mass is 50 kg upwards. Again, you have a lot of question marks above your head. What do you mean by 50 kg upwards? But even tell me a direction, it doesn't make sense. Okay, so this kind of quantities that do not make sense, or rather do not require a direction to make sense, is what we call scalar quantities. Okay, so for instance, yeah, here just now we mentioned 5 kg here. This guy must be a scalar. Okay, so we have already one example of what a scalar quantity is, which is mass. Right, so in this table here you can see, okay, so for scalar quantities it only has a magnitude. Of course, units, that is taken for granted. Yeah, you need to have units. Okay, so example, mass, length and time. Okay, all these kind of quantities, it makes sense without units. But vector quantities, you need both magnitude and direction. Very importantly, you need to tell me in which direction. So in the last, or rather in chapter 3, we have learned about forces. Okay, forces, I can push an object to the left, to the right, forward, backwards. Okay, I need to give a direction. In this chapter, we will learn two other vector quantities called displacement and velocity. Okay, so these are displacement, and as you can see at the start of the title of this section, is distance versus displacement. Okay, so they are kind of similar concepts. Displacement is quite similar to distance. In this case, our distance is a scalar, while displacement is the distance vector counterpart or cousin. So one is a scalar, one is a vector. Okay, alright, so let's come to distance versus displacement. Both have SI units of meters, so they're kind of similar. Right, so let's look at the definition to begin with. Okay, distance is the total length covered by a moving object along the path taken, while displacement is the straight line distance covered by a moving object regardless of path taken. Now what does it mean? Okay, this diagram sums up everything. Okay, if I have a car traveling from point A to point B, and the car takes the path of this blue line here, right? Okay, so the distance covered, so called by this line, is 7 kilometers. Okay, while point A and point B here is at a distance of 5 kilometers if you just take the straight line here. Okay, so now in this case, what is the distance traveled by the car from point A to point B? Answer is 7 kilometers. Alright, your distance is 7 kilometers because it took the blue path, the curvy blue path, right? But what is the displacement in this case? Recall the definition. Displacement is the straight line distance from the starting point to the ending point. The answer is 5 kilometers because A is the starting point here and B is the starting point. I don't care what path this object takes. The object could take this weird path. Alright, this weird path. So long as it starts at A and ends at B, the displacement is always 5 kilometers. But the distance is totally another thing, right? So let's remove this ugly looking like line. Okay, moving on. Okay, so not only are the numbers different, but because displacement is a vector quantity, technically you need to provide the direction. Okay, so this time around from A to B, the displacement is 5 kilometers to the right hand side. Okay, but in an exam, if they ask for displacement, we don't really need to give the direction. It is fine. Okay. Okay, let's try an example on the difference between distance and displacement. Yeah. Okay, so let's read the question here. John is traveling from point A to point C. So A is the starting point while C is the ending point. Yeah. On the way, he passed by point B. So you can see that John traveled from A to B and then B to C. Right. So what is the distance covered by John? Okay. So remember that distance is the actual path taken. It's the length of the actual path taken. So it's 6 plus 5, 11 meters. Yeah. But the displacement, we don't care about the path. It's only from the starting point to the ending point straight up. So it's 8 meters. Okay, so I hope this makes it clear. Okay, if it's not, if it's clear to you, then this exaggerated example will test your understanding. Okay, so a car takes a round trip around town and returns back to the same spot as it started. So the starting point and ending point both are at A. Okay, and the path taken is this curvy path, 999 kilometers. So what is the distance traveled? The distance traveled is 999 kilometers because that's the length, so-called the length of the actual path taken. For the displacement, now what is the displacement? Remember they ended back at the same spot. So it must be 0 kilometers. Okay, because the starting point is the ending point. So there's no distance, so straight line distance between the starting and the ending point. So I hope these two example covers the concept between distance, the difference between distance and displacement. Now displacement is a very weird concept. It's not just simply distance with a direction. Okay, so please bear that in mind. Okay, once you understood that, let's move on to the section 2, speed and velocity. Now if you look at just now distance versus displacement, you know that one of them is a scalar while the other one is a vector. Likewise, speed and velocity also behaves in the same way. In this case, speed is the scalar and velocity is the vector cousin of speed. Okay, so let's look at the success criteria for this part. In this section, we need to learn to state the difference between speed and velocity, the difference, and calculate this thing called average speed. Okay, let's get into it. Now, speed and velocity, they are quite similar quantities, so they both carry the same units, meter per second, SI units. Yeah. Okay, so let's look at the two definitions side by side. Speed is the distance moved per unit time. Okay, while velocity is the rate of change of displacement. So you can see distance and displacement appear here. Now, if you memorize the definition, you would very quickly see that the formula actually describes, rather the definition describes the formula. Can you see that speed is the distance traveled per unit time, distance over time? Okay, d over t, while velocity is the rate of change of displacement. Okay, so you can see here, speed is related to distance, while velocity is related to displacement. Just simply divide by the time taken. Okay. Alright, so speed is the scalar because, in case you're interested in knowing, because distance is a scalar, okay, so speed must be a scalar. Since displacement is a vector, velocity must be a vector. Alright, okay, so let's try using the same examples as just now. Okay, let's start from this one. Again, John, okay, moving from A to C, passing by B, right? So now it takes 30 seconds for John to do so, to travel this path, yeah? Okay, so what is the speed and velocity of John? That is the question. Okay, in the previous part, we already know that the distance traveled by John is 6 plus 5, 11. So what is the speed here? The speed here is 11 over 30 seconds, 11 meters over 30 seconds. And that gives me about, let me summon my calculator, yeah? If you're fast, please go ahead. Okay, it's approximately 0.367 units meter per second. Okay, remember your final answer should always be given rounded off to 3 sig fig, no fractions in signs. Okay, Now displacement, just now we already discussed, displacement is a straight line distance from the starting to the ending point, right? Starting to ending point, and that's 8 meters. So what is the velocity here? Now the velocity is displacement over time, so instead of 11 over 30, it's now 8 meters over 30 seconds, right? So if I do the calculations quickly, it will be approximately, so this one is approximation, 0.267 meter per second. If you wish to, you can always give the direction, no problem, right? So you can see that the speed here and velocity is different because distance and displacement are different numbers. Okay, moving on to back to this exaggerated example. Okay, again, round trip around the town and arrives back at the same spot. This time it takes 10 hours for the cars to make this round trip. So the distance we already knew just now, 999 kilometers. So what is the speed? Simply take the distance, divide by time taken, and you get yourself 99.9 kilometers per hour, right? Simple, this one already know. But here comes the interesting part, right? Displacement is 0 kilometers. So what is the velocity? 0 kilometers over 10 hours equals to 0. Almost as if the object did not move at all, which is true because the object came back to the same spot, yeah? So the velocity in this case is 0. So do take note of the difference between speed and velocity. Okay, so let's try this example here. Challenge question. Okay, the world record of 400 meters dash round a standard Olympic track. Okay, is the world record time is 43.03 seconds. Calculate the speed and velocity separately, okay, of this record holder. Okay, so for speed, we know very simple. Take the distance over the time taken, which is this, and you get yourself 9.30. Remember, it's 3 sig fig, yeah? 3 sig fig. Okay, now the velocity. This is when it's tricky. Now, if you look at a standard Olympic track, okay, you will know that it looks something like this. It's a terrible drawing, but okay, typically starting point is here. So where is 400 meters? If you know the Olympic track, you will know that one round, full round round the track is exactly 400 meters. Okay, so this record holder ran 400 meters from the starting point and back to the same starting point again. So the displacement must be 0. Okay, and hence the velocity is 0 meter per second. Almost as if the person did not move at all, right? Which is pretty weird, but this is what velocity means. Okay, so state an assumption that you made when you calculate the speed. When you calculate this number 9.30, what is the assumption that you made? First of all, if you don't know what is assumption, it comes from the root word assume, right? Assume. What do you understand by the word assume? Okay, means you take certain knowledge for granted. Okay, so assumption is a knowledge that you take for granted, that is taken for granted. Okay, so for instance, what do I mean by that? Okay, so for instance, if you see someone saying the Singapore pledge or singing the Singapore national anthem, you will probably assume that the person is Singaporean, right? Because, well, more often than not, someone who sings the Singapore national anthem is probably a Singaporean, and non-Singaporeans probably will not sing that. But you know that's not always the truth. You can have a foreigner who is, just interested in the song, learning how to sing. That's it, right? So assumptions, being assumptions, may not always be true. Okay, so let's see. So in this case, what is the assumption that you made when you calculate the speed 9.30? Well, the answer is you assume that the person runs at a constant speed of 9.30 meter per second throughout the whole race, right? Okay, so the assumption here is the runner runs at a constant speed. Throughout the race. Right? Right, it makes sense because if sometimes he runs faster, sometimes he runs slower, then we cannot simply say that the speed is 9.30 meter per second. Alright? Okay, so the assumption here is he runs at a constant speed throughout the race, but you and I both know that it is not realistic. It is not true. Because if you look at the Olympic track, right, there is a bend. And anyone with experience running, right, especially sportsmen and women, you would know that, coming to this turn, you will actually slow down. Right? Or rather at the starting point when you just run off, right, you'll probably be slower than, for example, here when you're running at a faster speed, right? So you realize that realistically, right, in real life, objects may not, it's unlikely to travel at a constant speed throughout a journey. Think of a car, right? If I'm traveling from town A to town B, from Sengkang to Punggol, for instance, right? I can't be always traveling at 60 kilometers per hour throughout. Why? Because, for example, there's traffic light that I have to stop at, right? I have to stop. Sometimes when there's a car in front of me, I have to slow down, right? Or go faster if I want to overtake the car. So in this case, this constant speed assumption is not realistic. So how? The next question is, so how? If the object is not traveling at constant speed, can I still then calculate the speed of the object? The answer is yes. This is the next part. We use average speed, right, or average velocity to indicate what is the so-called speed of the whole journey for this object. Okay, so average speed, well, it's also a speed. It also carries the units of meter per second. Okay, so in reality, we know that objects don't always travel at the same speed from point to point. So no choice, we have to calculate this thing called average velocity. Okay, so let's take a look. Average speed or average velocity. Yeah. So average speed is the total distance traveled over total time taken. That means I do not care what is going on in between. I'm just concerned about the total distance and the total time taken. Right. Okay. Average velocity is the final displacement. That means the ending point. Right. The starting to the ending point. Ending. Right. I don't care what goes on in between. I'm only interested in the starting to ending point over total time taken. Okay, so let's look at a typical example where you are told to calculate the average speed. Okay, now this type of question, you may have encountered this in lower secondary mathematics. Okay, now this type of questions comes, the journey described in the question comes in two parts. Okay, let's look at it. So a car travels from town A to town B, which is 100 kilometers away. The car takes 30 minutes to travel the first 50 kilometers. So you can see, right? The first part of the journey, 50 kilometers. Time taken, 30 minutes. Okay, the car then completes the rest of the journey at a different speed. Okay, so that's the second part of the journey. And you are tasked to calculate the average speed for the whole journey. Okay, now, of course, this type of question, since there is two parts to the journey, what I recommend and I suggest everyone to do is to draw out this diagram over here. Okay, now in this diagram you can see there is part 1 and part 2 of the journey, and I actually listed down the information for each part of the journey over here. Okay, now I suggest to do this because if you're able to fill up all the information, distance, time and speed, for each of the two parts, you can actually answer all, if not most, of the questions that comes. Okay, so let's do this together one time. Okay, so for part 1, distance is 50 kilometers. This is given in the question here. Okay, time taken, half an hour, 30 minutes. Why do I convert 30 minutes to half an hour? Because you realize that the speed here given is in kilometers per hour. Can you see that? Kilometers per hour. So clearly I must work in hours, right? All the time. Okay. So speed is distance over time. This one we already know. Which you press your calculator correctly, it should be 100 kilometers per hour. Okay, I'm running out of space, so I'm writing over. Okay, so we are done with part 1. Part 2, distance is 50 kilometers because from start to end is 100. So we know that it's 50. Time we don't know, but we are given the speed 80 kilometers per hour over here. Okay, so what's the time taken? Okay, recall from the formula speed equals to distance over time. We manipulate the algebra a bit to get time equals to distance over speed. Okay, so let's put in the numbers. Time equals to distance over speed, 50 over 80. That gives us okay, 50 divided by 80, that is 0.625. 0.625 hours. Okay, everything is in hours in this question. Alright, so we are told, remember, we are told to calculate the average speed for the whole journey. So let's look at the formula. First thing is to write down the formula. Average speed equals to total distance over total time taken. Do we have all the information already in the diagram? Actually, yes. Right. Total distance is nothing but distance of part 1 plus distance of part 2. Total time taken is time taken for part 1 plus time taken for part 2. And there you go. You just need to put in all the numbers and you should get the answer. Okay, so this diagram here to me is very, very useful. Please draw it on your own. This won't be provided in exam, of course. Alright, moving on. This is just an example for you to try. Alright, all you have to do is put in all the numbers, try to figure out all this. Okay, figure out all this. Okay, and you can try on your own. The answer is 50 kilometers per hour. Alright, if you're not sure, you can then consult your teacher. Okay, but first of all, I need to let everyone know that for this part here, the driver takes a 15-minute break at the station. This 15 minutes is to be taken into account for the whole journey because it's part of the journey. Hence, I have part 2 over here. Part 2 over here, you realize that the distance is 0 because it's taking a break. Time is 15 minutes, 1/4 hour. You need to take the time into consideration when you calculate the average speed for this journey. Okay, so far so good. Let's move on. Okay, so we, up to now we have learned a couple of things. We have learned scalar versus vector. What is the meaning? Okay, under scalar we have distance, right? Distance versus displacement. Okay, we also have speed versus velocity. Okay, again, one is a scalar, one is a vector. We also have average speed versus average velocity. Okay, average velocity is hardly tested, so I'm not taking into account of that. Okay, so the next concept we need to know is called acceleration, right? Now, if you already know a bit of science, you will know that acceleration is sort of like speeding up. Okay, something like speeding up, yeah? The speed will increase. Okay, so in this section we will learn what's the definition of acceleration, and we will calculate using this formula change in velocity over time taken. Okay, we will state the meaning of what is uniform and non-uniform acceleration. Okay, let's get right into it. Acceleration carries the unit of meter per second square. How do you know that it's meter per second square? Okay, in order to do that, we have to know why, we have to look at the formula first. But before that, acceleration is the rate of change of velocity. Okay, so if you look at the definition, you can figure out that the formula is like this: change in velocity over time taken, or in symbols, delta v over t. Now this triangle thing, don't be afraid. it just means change. This thing here means change in. So don't be afraid. Okay, so delta V is equals to V minus U. Now you see that there are two letters here, V minus U. V means final velocity, or simply said final speed, over minus initial or starting speed. Okay, so in this section I will use velocity and speed interchangeably or loosely, but you know that there's a difference between the two of them. Okay, so triangle sign or delta means change in, and V is the final, U is the initial speed. Okay, alright, so with these two you can always combine these two formulas to get the final formula A equals to V minus U over T. This is something that we will use even more often, okay, than the rest. Okay, so let's try a simple example. An object accelerates uniformly from 10 meters per second to 50 meters per second in 10 seconds. Calculate the acceleration. Okay, so in this case, we know that okay, A equals to V minus U over T. So it's a matter of what is V, what is U. Okay, so if you recall, V is the final speed or final velocity. Okay, so in this question, which one is V? If the object accelerates from 10 to 50, then 50 is the final, 10 is the initial. Okay, so all you have to do is put into the formula. Okay, here I use delta V, or simply if you don't like this, you can always use this formula, A equals to V minus U over T, that is equals to 50 minus 10 over time taken 10 seconds. Okay, that will give you 4 meter per second square. Oh, by the way, I have not discussed why is it meter per second square. Okay, so if you look at the formula here, V minus U over T, right? Okay, so you see units. Okay, so units of A, okay, equals to units of V minus U divided by units of time. So V minus U carries the units of meter per second because it's a speed, and unit of time is s, seconds. So that gives you meter per second square. Okay, this is how you get the unit. Not important, you can choose to memorize. Okay, so in this next part, okay, another object accelerates uniformly. Now they give you the A. A is 5. Okay, from a speed of 10. From a speed of 10. So this one gives me the U, initial speed. The object accelerates for a time of 20 seconds. That gives me the T. Find the V. Okay, so again, quote the formula, plug in the numbers, and you should get the V. Done. Very simple. Okay, now this one is a real life application question. Okay, in 2020 I googled. Okay, if you disagree with me, if you are a sports car fan, I'm sorry, I googled this information. Okay, the fastest car, okay, could accelerate from rest. From rest. This tells me that U is 0. Okay, to a speed of 26.8. That is the V. Within the time of 2.3. Okay, calculate the acceleration. So A equals to V minus U over T, where V is 26.8, U is 0, time taken is 2.3. Okay, 26.8 divided by 2.3, that gives me 11.7. Approximately 11.7 meters per second squared is the units of acceleration. Hence, find the time taken for it to accelerate from rest, again from rest, U equals to 0 to the final speed of 44.7. Now the time is unknown. Okay, time is unknown. So again, let's go back to the formula. A equals to V minus U over T. Now we need to make T the subject. T equals to V minus U over A. Okay, So that equals to 44.7 minus 0 because it's from rest. Okay, now over here the t I'm not going to use 11.7, I'm going to use 11.65 because 11.7 is a rounded off number. Okay, so it's 11.65, so my answer should be it's about 3.84 second, yeah, because time. Okay, so we are done for this part. Okay, the next concept, okay, the last concept for this video, we're almost done, is called deceleration. Now deceleration, you probably already know, means slowing down. Okay, opposite of acceleration. Okay, so for deceleration we also use the same formula, which is a equals to v minus u over t. Okay, but don't change a to d. Doesn't mean deceleration means we use the letter d. No, we use the letter a as well, but the difference is if the object is decelerating, if you use the formula, we will get a negative number for a. Okay, let's look at an example. What do I mean by that? Okay, an object changes its velocity from 10 to 6. That means starting u is 10, finally is 6, yeah, within a time of 10 seconds. So you can see from 10 to 6, this is slowing down, right? So decelerating within a time of 10 seconds. Calculate the deceleration. So again, using back the same formula, now please take note, v is 6, while u, sorry, instead of v is u is 10. Okay, so now it's 6 minus 10. That gives me a negative number. Okay, so here's the thing, if you use a equals to v minus u over t and you get a negative number out, this negative sign tells us that it is deceleration. Okay, deceleration. No, I spelled it wrongly, sorry. Deceleration. Okay. Alright, hence when we are the acceleration is negative, okay, but the deceleration, we just take the positive number will do. Okay, so if we are asked for the deceleration here in this case, we just quote the positive number. Okay, so yep, we simply take the positive value for the acceleration if we are asked for deceleration. So that's it for this video. Okay, in this video we've learned quite a lot of stuff. Yeah, we have learned, first of all, we go back to the idea of the mathematics, how to find the equation of a graph by first finding the gradient and then the y-intercept. Okay, so that's the mathematical part that we need. We then move on to talk about scalar and vector quantities. Okay, remember that for vector quantities, I need a direction. Yeah, but scalar doesn't require a direction. So for the case of distance versus displacement, distance is the scalar, while displacement is a vector. Okay, the vector cousin of distance, right? But we also learned that displacement is not that simple, not just distance with a direction, but rather displacement is the straight line distance from the starting point to the ending point, regardless of what path is taken, right? So because of this idea, we realize that, oh, there are some weird cases, right? If I start off at a point and I end back at the same point, it's as good as I did not move at all. Okay, so displacement is 0 for this case. Next, we talk about speed versus velocity. Okay, again, one is a scalar, one is a vector. We know that we learned the formula. Speed is related to distance, while velocity is related to displacement. Okay, so in this example, we learned that, oh, because of the weird nature of displacement, like here, okay, so it's almost as if the car did not move at all. Alright, okay, then we also talked about average speed and average velocity. Okay, remember that we need this idea because objects don't always move at the same speed throughout the journey from point to point. So no choice, if you want to describe a so-called speed for a journey, we have to use average speed and average velocity. Okay, so this is the type of typical question that they will use. Remember to draw this diagram to separate the journey into part 1 and part 2, and then fill in the information. Finally, we discuss about acceleration, which is like speeding up. Okay, so it's change in speed over time taken, where change in speed is final minus initial. Okay, final minus starting speed. So lastly, for deceleration is the opposite of acceleration. It's just that so you will use the same formula, just that if it's a decelerated motion, you will get a negative value. Okay, it will be negative. So if you ask for the deceleration, we simply quote the positive value of it. So that's it for this video. It is very intensive and very long. I hope you learned something. Okay, please review again and check whether you understood or not. If not, thank you for watching. I'll see you back in class. Take care.